Monad is the most intimidating word in programming, and it can quickly get out of hand. Imagine this situation. You are on a job interview, you receive a question to complete some class, and then you say, "Excuse me, would you mind if I used a monoid in the category of end-of functors to complete this method? I see a very effective solution." However, there is a twist in this story. Assuming that you are a C# programmer, then I guess you would like if somebody told you that there is the whole bunch of types built into C# which are proper monads by the book. And that's not all. You don't need to know the theory. You are using those types every day. And you are doing that in a proper monadic way. In this video, I will show you those types that are monadic in C#, and I can assure you that you will never view those C# types with the same eyes again after you hear this. So this is the first monad I will create, the enumerable of integers. The process of initializing an enumerable to contain some value is what the theory would call a unit operation. We are, again, by the theory, we are lifting a value to become something more, to become an enumerable that serves that value when you iterate it. You can imagine having a function like this. Get prime divisors. It's taking a value and returning an enumerable of values. So it is turning a value into a monad. It is lifting it again. You can use the link select many operator and pass a function that converts each element into a monad itself. This operation is in theory called bind. Select many is the bind operation on monads. That's it. This is a proper monadic way to use an enumerable. Let me show you another traditional monad, a func delegate. I will assign it to a lambda that returns the same value the enumerable served when iterated. Every monad is capturing one responsibility, one concept, and applying everything that comes with that concept to the value or values it contains. Enumerable lets you iterate through integers, but func defers the calculation of the value it returns. So when you assign a delegate to a variable, nothing happens. It's a very quick operation that does nothing. And then you can apply bind again. Look at this. I will create a new lambda that calls this first lambda as a part of a larger operation. This is the chained call of lambdas. But this is a proper bind operation using the syntax of the C# programming language. What you must understand here, which is very similar to calling select many above, is that again, nothing happens. I'm just declaring the operation. Nothing executes, only an assignment. Nothing happens until I invoke the lambda. So the func delegate is a monad that gives you the ability to defer execution of some code. Let's raise the bar. Even heavier situation is when you want to do the same thing asynchronously, the task monad. What would be the bind operation on tasks? Await the result of one monad, one task, but then wrap it into a completely new async lambda. If I executed that lambda, that would return the task. So this is the bind operation. It's red because the compiler has a hard time to understand the type of this lambda. So let me give it to the compiler and it will be happy. don't leave yet, this is terrible, this code is, oh, you will never write code like this. But in the very next line, I will show you what you will really do. Your situation will be almost always much simpler than what I did in the line above. You will just await a monad, a task, and use the result in an operation such as console write line. Await is a syntactic sugar that lets you apply bind to tasks. It used to be much more complicated in the time when we had task-based parallelism in C# in .NET, but had no await, async await keywords. But then comes the extended theory. For example, imagine that you have a function that knows nothing about monads. A square of an integer. I've been working with integers through the entire demo, but this particular function knows nothing about enumerable, func, or task. It just knows about int. You can use regular functions in monadic operations. For example, you can use the select operator to transform each element of the sequence into a new element of the new sequence. Therefore, again obtaining a monad, a new monad, which is different from the first one, by applying a non-monadic function to the first monad. I don't know if I can repeat this sentence, but the point is that this operation has a name. It is called map. Then what is the map on tasks? It is the continue with method on task. That is a proper map function defined on the task monad. If you ever use it again in the times before async await, you were using tasks in a proper monadic way. Do you see how monads are sneaking into your code, making you start thinking differently? Each monad again is capturing one responsibility in one context and doing that responsibility with a vengeance so that you don't have to think about that. Your job is to think about functions like square, do things that know nothing about monads, and then apply those functions to monadic objects so that they add that context and that responsibility to your operations that are simple. Let me show you another very interesting monad. Nullable types. Look at this. I have got a string that is assigned. It's not non-null string, but it is assigned to a nullable reference. If I wanted to get the length of such a string, I can only get a nullable length. And I would use the null propagation operator, dot length. Guess what? This is the map operation on nullable strings. I could turn a nullable string to upper to again obtain another nullable string that is another nullable map operation. It's very simple. However, nullable references do not have the bind operation implemented in core C#. Let me demonstrate that. You could have a function that receives a non-nullable string but returns the nullable one. This function would be a subject to bind, but there is no such operation on nullable, no operator on nullable references in C#. Let me show you. I have to check whether the upper nullable string is null manually and then either return null or call the cap, because cap only accepts non-nullable strings. I must protect it from making a call on a nullable string. I will now implement a complete monad for you that operates on nullable objects. Before I show you that magnificent code, which will be about 10 lines of code, I would like to remind you that this channel is free and all the videos on this channel are free, but only thanks to the people who are sponsoring me on Patreon. So if you like what you're learning from this video and other videos on my channel, then please consider joining the community on my Patreon page. That will give you access to the source code of this video and all other videos, some other goodies that are not available on YouTube, and you will surely help me maintain this channel free forever. Thank you very much. Now, turning incomplete nullable reference types into a complete monad. The first thing we must define is the bind operation. It accepts a function, a delegate, that receives a common object and returns a monadic version of that type. I could also use a different return type. Bind method can change the type of the result. I will leave that for you to think about that. I will do that in the map operation just to show you that it's very simple. What if the type T is not a reference type? We use the nullable struct because that is another monad, proper monad in C#, which captures nullability, adds the nullability capability to value types which can never be null. I will now add the corresponding implementations on nullable value types. So there will be the bind, the map, and the map to reference type, which turns a nullable value type back to a nullable reference type, so I have completed the full circle. The last operation that is very convenient, not necessary in theoretical sense, but very convenient, that is the match operation. It is usually called match. It would let you access the value, but it is your duty to specify both variants now, because the value might not be there. You can imagine having a whole bunch of other functions that operate on strings, such as the one turning into upper or the one getting length of the string. But these functions can be all monstrous. Those can be business methods you have developed, tested in isolation, done all other kinds of things using those functions or methods. The point is that they know nothing about monads. They don't know that they might apply to a nullable reference. They do not apply to a nullable reference. That is a separate concern. Now you use them. I will turn a nullable string by bind to a nullable uppercase string. Next operation, cap it. Then map to a value by applying get length. This would be a nullable int. And ultimately, I would match whatever the integer nullable int I have against two patterns. One, if I do have a length, I would just say this is the length. Otherwise, if I don't have the length, I would say it's null. We start from a nullable string hello, then we get the nullable string hello in uppercase. Then after capping, we have a nullable string which is null. Which means that get length, now comes the twist, get length won't be invoked. But eventually, after a match, both null and non-null nullable int would be converted to a proper string. And it will be the string telling I'm null. I know that I will always have a non-nullable string which I can print on the screen. Do you see? You have been using monads in C# all the time, whether you knew that or not. I hope this has given you some background, and as I said, that you won't be watching these types with the same eyes again.